Okay, welcome back everybody. Today we're going to be looking at the ionization energy and periodic trends. Your two learning targets for today is one, I can describe the periodic trend for the first ionization energy, and two, I can describe the cause for the observed periodic trend. All right, looking at your note pages that you have out in front of you, we have a couple of concepts or terms that we need to cover before we dig into this concept. The first one is, let's define what ionization energy is. Ionization energy is the amount of energy required to remove an electron. The other thing that we need to look at is Coulomb's law. Now, we've investigated Coulomb's law prior to this unit, so just to make sure that we have a good understanding and so that we can apply Coulomb's law to the observed periodic trend, I wanted to cover it again here. So remember that the force between two electric charged particles is proportional to the product of the two charges divided by the square of the distance between them. So that we can summarize that as the force is going to be proportional to the charges, the two charges, which we'll label Q1 and Q2, divided by the distance squared. And we'll use R for that. Okay, so let's go ahead and look at our graphs. And what I'm going to do first is I'm going to help us by labeling some of the key parts on this graph. Will help us better understand what we're seeing. So let's label the peaks first. And so if we start with the peaks, the first peak here at the top is the second atomic number, which of course would be helium. Then my valley that immediately follows it is atomic number 3, which will be lithium. We'll label the peak at 10 as neon. Sodium is number 11. Argon is number 18. Potassium is number 19. And then the last one we'll label over here will be our krypton at number 36. Okay. So now let's look at a trend, and let's look at for the first trend when we're going across a periodic table from left to right. So as I'm moving from left to right, and let's start on period 2. Period 2 begins with lithium here and ends with neon there. So generally speaking, as we move from left to right, from lithium to neon, we see an increase in the first ionization energy. If we look at another period on the periodic table, and so let's look at period 3. Period 3 begins with sodium on the left and goes to argon on the right. And so we see, as we go from sodium to argon, again, we see that trend. And again, you can see it between potassium and krypton for period 4 on the periodic table. So on our worksheet, let's go ahead and label the ionization energy trend for across a period. And across a period, we would say that the first ionization energy is going to increase as we go from left to right. The next thing that we want to investigate is what happens down a group. well, and I'm going to change colors again here. Let's see if, let's use green. As we go from down a group, if we start with the noble gases, and you'll notice that all of our peaks in our graph are noble gases, if we just give a general trend, well, neon's lower than helium, argon is lower than neon, and then krypton is a bit lower than argon. So our trend for the noble gases, as we go down a group, the first ionization energy is decreasing. Now let's check another group. Another group to check that's relatively easy on this graph, but we could pick any group. But I'm going to go ahead and pick the alkali metals, the first group on the periodic table. And we see from lithium here, it's only a slight decrease, but it is a decrease. And then from sodium to potassium, again, we see that decrease. So let's go ahead and label that one on our worksheet. As we go down a group, the first ionization energy tends to decrease. Okay, so we have answered, the first one is basically understanding the trend of first ionization energy. To review, as we go across a period from left to right, ionization energy tends to increase. As we go down a group, the first ionization energy tends to decrease. All right, let's go to page 2 on our worksheet. Now we're going to look at a little bit more in depth of why, and try to explain why the first ionization energy as we go across a period is going to increase. So remember, as we tend to, as we look at the first ionization energy across a period, we're going to say that this tends to increase as we go from left to right. So I want to look at that a little bit more in depth. And to do that, I want to look at some Bohr diagrams. And I've drawn some Bohr diagrams quickly for you. I think Bohr diagrams help us understand what's happening at the atomic level. And so the three that I chose from period 3 on the periodic table is sodium, silicon, and chlorine. So remember that sodium is atomic number 11, so it has 11 protons. And being neutral, it would also have 11 electrons. Silicon's atomic number is 14, so 14 protons and 14 electrons. And chlorine's atomic number is 17, so 17 protons and again 17 electrons. Now remember, as we go this way on the periodic table, ionization energy, which I'll just abbreviate IE, is increasing. So can we think of some reasons why they're increasing? And remember to think about Coulomb's law. And so as we're moving from left to right, notice that the charge differential of our nucleus is increasing. So as we move from left to right, the number of protons in the nucleus is increasing. And the number of electrons does as well. But what I wanted to notice is that there is a shielding of 8 electrons in our core electrons for each of these elements. So our effective nuclear charge essentially is increasing as we move from left to right. So as we look at Coulomb's law, we're increasing the charge differential, and therefore the force of attraction between the opposite charged particles, the positives in the nucleus and the negatives for our one valence electron that's going to be removed, or the first valence electron that's going to be removed, that attraction is increasing. So therefore, it will require more energy to remove that electron. All right, go ahead and answer that in your worksheet, and we'll go to the second question. The second question, obviously you can pause the video and answer that there. But when we get to the second question here is explain using the atomic structure and Coulomb's law the observed ionization energy trend down a group. So just to recall, as we go down a group on the periodic table, ionization energy also is going to decrease. All right, let's see if we can't look at a Bohr diagram for down a group and see if we can understand what's happening here. Now, what's happening here may appear to be a little bit more obvious. As we are looking at our elements, the thing that I'm noticing right away looking at a Bohr diagram is that the outside electron, the first electron that's going to get removed, so our first ionization energy, that first electron for lithium here is on the second energy level. The one for sodium is on the third energy level. And the one for potassium is on the fourth energy level. So each time as we progressively go down a group on the periodic table, you see that that valence electron is further and further away from the nucleus. Remembering Coulomb's law that stated we're going to divide by the square of our distance, so our ionization energy, or that force of attraction that holds that electron in, is going to be less as that distance between those charges increases. So remember, you have your positive nucleus, you have your negative electron. As that distance increases, that force of attraction is going to decrease exponentially, right? It's a inverse square rule. And therefore, this is the reason why you would have a decrease in the first ionization energy as you move down the group. All right, again, go ahead and pause, rewind that, and fill in your answers for the worksheet for that question. I'm going to go ahead and then give you a little bit of a homework assignment or assignment for you to research or come up with on your own, and here's the two questions. The first one is, make a claim to explain the dip in ionization energy observed for element 5, boron. It will help you to look at the orbital diagram for each element. So just make sure I'm explaining what I want you to look at. Let's go back to the graph. If I go back to the graph, I'm going to, and I'll do this in a different color. Let's use orange this time. We see here, right at boron, that you have a dip in ionization energy, which is counter to the trend that we observed. We also see that dip here for when we go from nitrogen to oxygen. So your two homework assignments, and I'll go back to them now. Your two homework assignments are something I want you to come up with on your own. Is one, make a claim to explain that dip and why it's occurring at boron. And two, make a claim to explain why we see that dip again at oxygen. My clue or help that I want to give you is to look at the orbital diagrams for each of these elements. That might give you some hint into what may be happening. I'll go over this in the next video, but before then, please have that completed. Thanks for tuning in today, and come and see me if you have any questions.